All right, so in this very short presentation, I'm going to very briefly introduce you one of the project that we are developing on full waveform inversion, this imaging technique used in the seismic community, where you try to take into account the mathematical model of wave propagation using that information to get better imaging results. So the title is Robust Optimization and Machine Learning for Full Wave Inversion. So the project is really about combine mathematical and algorithmic results in inverse problems and the computational resources that we have at Xofia to implement a robust computational inversion framework for full wave inversion. The main idea is to couple wave-based imaging method with machine learning techniques based on deep neural networks to reduce the computational complexity of the inversion process and also keep the advantage of full wave imaging in its imaging capacity. That is, we want to be able to do very fast, robust inversion without sacrificing the quality of the imaging. Okay. So the talk is going to be very mathematical. I don't intend to talk about all the details, but only the main ideas. All right, so very quickly, this is just to motivate the idea. So you have this wave equation that describes the propagation of seismic waves, and you have some data which are solution of this wave equation essentially. So from this data, you want to recover the velocity field of the wave. Okay, that's what the objective of full wave inversion. This is a full nonlinear case in a sense that you are not just trying to identify reflectors, etc., by assuming that you know the background velocity. Here, we try to recover everything in the same frame parameters. Okay, so the general classical way of doing this inversion is to formulate it as a least square problem. So basically, you try to fit the model to your data. Okay, so you have a model that give you a prediction if you know the model parameter, and then you have measurement data. So what model parameter give you the right data? Okay, that's the objective. And the classical way of doing this is to do least square. That is, to minimize this mismatch between your model prediction and the real data. So this is a picture that shows you a true velocity model imaging with the classical least square formulation and imaging with a new formulation that is based on some robust imaging method, robust optimization method that is based on optimal transport theory. So you see the dramatic difference between these two types of reconstructions. And we want to focus on the part where you have this robustness there. All right, so this is a very, very mature technology in terms of its mathematical foundation and algorithmic development. The main problem is implementation. So here we have a very general framework that allow us to put various method of robust optimization in the same framework by doing some tricks like what I show here. That is basically finding some operators that is essentially approximate to the inverse operator of the wave propagation process, and use that to preconditioning to make your problem nicer. Again, you don't need to worry about the details, but I just want to convince you that we have an idea that can put all these robust optimization framework into this modified least square framework, so that we can use existing optimization methods to solve this to solve the minimization problem for imaging purpose. The question remains is what type of robust method we can include in this. That is, what type of operator that I mentioned that we can use to in this framework. It turns out that the optimal transport-based method that I just mentioned a minute ago can be included here. All the existing robust optimization based on prior knowledge, et cetera, can be imposed here. So, for instance, in the linearized case, what I'm talking about is basically a classical way of preconditioning yield-conditioned problem. Okay, but that is again not its full potential. Its full potential lies in the full nonlinear case. Okay, so the next element of this game is to find a good candidate of this one of the efficient robust optimization method, and we have a strategy to use machine learning techniques to do that. And there are many reasons for doing this. I won't have time to talk about that, but a punchline is that for the machine learning framework to work in the usual sense, you would require very accurate training. For this framework to work in our case, you actually do not need perfect training, which make our method very flexible. Okay, so that is a summary of this idea. So with this robust optimization framework, assisted by this machine learning method, we have architecture here that I presented that can give us first a reduced computational cost because we train approximate inversion operator already. And secondly, the reconstruction result is not sacrificed, meaning that if you solve this minimization problem, you get the same solution as you have for the classical sense. So you don't sacrifice anything. So this is a general framework that we proposed to improve the current technology in this full wave inversion idea. So what we are currently doing is to implement this idea on practically important scenario, that is to use the accurate model of elastic wave equation in this as the wave propagation model, and also to scale up the size of the problem that we could solve. This depends on the size of the neural network we could train for the approximate inverse. But remember, we do not need to do perfect machine learning, which is impossible to do in the oil industry with practical data, because the data that you can use in this case is not enough to train such a huge network. But you can train something that is very close to a good one, and that is good enough. Okay, so we are working on the implementation side of this. Thank you.